Hello and welcome to our Friday seminars. It is my pleasure to introduce to you our speaker today, Dr. Jonathan Hobbs from CalJet. John is a data scientist there at the Jet Propulsion Laboratory at CalJet. He received his PhD in 2014 from Iowa State and had a co-major in statistics and meteorology. And he has varied research interests spanning both methods and applications. At JPL, his research mainly focuses on developing methods for uncertainty quantification for atmospheric remote sensing retrievals.
All right.
Including analysis of NASA's OCO2 and 3 data, which suppose he will tell us more about today. And he also has substantial experience in developing methods for spatiotemporal data with geoscience applications, including hydrology and carbon cycle science, among other things. Today, he's going to tell us about some of his recent interesting work on statistical inference for the global carbon cycle from space-based observations. So please join me in welcoming John.
Thank you very much for the nice introduction. And for the invitation to be here. I very much appreciate the hospitality thus far. It's been a really interesting and enjoyable visit. So I'll talk about statistical perspectives on inference for the global carbon cycle from space-based observations. So that I'm sort of going to cover a few different activities that we've done in this area through the course of the talk, and in the process talk about some of the data products that are related to this work. A lot of our charge from NASA at JPL is to produce data products for public use and use in science and applications, and so a lot of this methodological work is motivated by those objectives. So, brief outline. I'll give a little overview of NASA's Earth science programs and Earth orbiting satellite constellation, and then I'll talk about what I'm calling the level 2 inverse problem, which we'll spend some time developing and outlining, and I'll talk about what that means. A little bit of further detail on addressing spatial dependence in that problem, and then I'll wrap up with some discussion of the so-called level 4 inverse problem. So, okay, to get things started, a little background on NASA Earth science. The schematic on the left here is the so-called Earth System Observatory, and this is actually something that's in the works. About every 10 years, the National Academies puts together an effort that's called the Decadal Survey that NASA and NOAA and USGS in the realm of Earth science pay close attention to. And this survey basically outlines priorities for the next 10 years for observing the Earth system, and NASA pays particular attention to the focus on how to use remote sensing to monitor the Earth system. And so out of the last of these surveys, which came out a few years ago, the focus is on this Earth System Observatory, which has several areas of focus, which are in the different colors on the figure there. And this overall observatory is going to motivate specific priorities for launching instruments into space in the next 10 years or so. And so there's a number of interconnected systems that will be monitored. And remote sensing of the Earth is a really valuable tool for monitoring climate in particular. And over the past few decades, there's been a lot of instruments launched that have provided a lot of valuable insight for numerous climate quantities of interest. I've listed a few here on the slide. Key weather monitoring variables like temperature and humidity in clouds, trace gases in the atmosphere. We'll talk about greenhouse gases later on. Air quality, hydrology, as well as land cover and land use. And this now sort of spans multiple decades. The initial substantial effort a couple of decades ago was something called the Earth Observing System. The new one is sort of rearranging things a bit with sort of a variation on that theme. So here's another little schematic that gives a little more detail about the fleet of Earth observing satellites that NASA has particular that NASA is particularly responsible for. So on the sort of inner part of the spiral here are some of the earlier instruments that were launched in the late 90s and early 2000s. I've done some work with Aqua, which is there on the inner part of the spiral, and that has several instruments that that sort of work in concert for monitoring various atmospheric and surface quantities of interest. And then as we go out and around the spiral are some more recent missions. I think up there on the top is OCO2, which I'll talk about shortly. That's the Orbiting Carbon Observatory. And then on the bottom part of the spiral are some upcoming or planned missions that are in development, or at least have concepts that have been put forth. And then this little central part of the spiral right here are instruments that are on the International Space Station. And one notable instrument there is OCO3, which we'll talk a little bit about as well. The link there on the bottom is one of the data archive sites for these data products that are produced from these missions, and data from missions like OCO2 and OCO3 can be accessed there. So I think I hit on most of the points here, but I just wanted to mention that a lot of these satellite assets are managed by what are called missions. So most of them have an associated sort of project team and management structure that's associated with that particular instrument. So OCO2 is a mission, OCO3 is a mission. And usually these missions are informed by science objectives, and they're really substantial projects. So their development takes multiple phases across many years. And then their ultimate objective is, as I said earlier, to deliver publicly available science data products. So what are these data products? They're sometimes called Earth System Data Records, ESDR, and there's sort of a progression of these data products that are developed by the missions. And I'm going to talk about every mission sort of has its own vernacular and approach to doing this, but a lot of them sort of follow this overall structure, having 4 different levels of data products. And so level 1, there's an example of a level 1 data product here at the bottom that I'll talk about more later. Level 1 are sort of instrument level data, what the instruments are actually observing that have been processed to the units of the particular sensor. So like the example on the bottom here, this is basically the intensity of radiation observed by OCO2 in this case at a particular location and at a particular time. And so in this case, that's a function of wavelength. So the instrument observes at this collection of wavelengths, and that's essentially what constitutes a level 1 observation. Those level 1 products are used to derive level 2 products, and these are geophysical variables, usually atmospheric or surface quantities of interest that are essentially estimated from the level 1 data. And these level 2 products are usually at the same space and time resolution as the level 1. And so in the talk here, I'll talk about some of how that level 1 to level 2 processing takes place. And then level 3, sort of in terms of scientific interest, is sort of the same quantities of interest as level 2, but they're often sort of mapped to more user-friendly space-time grids that have some regularity in their space and time resolution. And then level 4 is some additional processing of usually level 2 or level 3, sometimes level 1, that involves some other kind of geophysical model. So some kind of data assimilation or other type of inference that makes use of the lower level products to come up with an additional quantity of interest. Okay, so I'm going to talk about what these different things mean in the context of the carbon cycle, which is the focus for OCO2 and OCO3. And there was a nice overview in JASA a few years ago by Noel Cressy, who's been involved in these missions some and put together a nice overview and statistical perspective on the pipeline for the carbon cycle. So at the bottom is a little schematic of the carbon cycle, and basically what these blocks are essentially different storage reservoirs, if you will, for carbon. So the oceans are a big one, and that this particular figure is kind of separated into the deep ocean and then sort of the surface layers of the ocean that are essentially interacting with the atmosphere. And then the atmosphere is also a big reservoir for carbon. The land is as well, and then they've separated out fossil fuel storage as well. And then the various arrows are basically some estimated exchange rates for carbon among these reservoirs. And these exchanges are what are called in carbon cycle science fluxes. And that's actually what ends up at the level 4 part of the problem here. Is the objective is to estimate these fluxes or rates of exchange between the different storage reservoirs. So a couple of things you might notice here is that the actual rates of exchange, particularly between land and the atmosphere and ocean and the atmosphere, are pretty sizable. But the relative to, say, the fossil fuel exchange. But what the fossil fuel sort of represents is a modest but noticeable perturbation to this overall balance among the atmosphere, ocean, and land. And that perturbation, if you sort of look closely, is kind of in line with a little bit of the variability among the other reservoirs, the ocean, atmosphere, and land. So the fossil fuel perturbation initially goes into the atmosphere. Some of that ultimately ends up back in the oceans or in the land. But one of the big uncertainties in carbon cycle science in recent years and going into the future is how much of that fossil fuel perturbation will continue to go back into the ocean and land, and how much of it will remain in the atmosphere in the form of carbon dioxide, which of course is a greenhouse gas. So that's kind of the science motivation in these remote sensing of greenhouse gas missions. More formally, the progression of data products for the carbon cycle. At level 1, we have the so-called satellite radiances. We're going to call those Y in the rest of the talk here. And these are at the resolution of a particular satellite footprint. And then at level 2, we've got something we call a retrieval, which gives us an estimate of CO2 in the atmosphere. And that we'll call that X hat. At level 3, as I said on the last slide, we might aggregate those in some fashion in space or time, and we'll call those X tilde. So that's kind of the progression. We're going to focus mostly on level 1 and level 2 in the talk here. And to motivate that, a little bit more about OCO2 and OCO3. So on the right, in the schematic here is a little sort of overlay of the observing pattern of OCO2. And so the little rectangles are individual footprints from that constitute basically a single snapshot or a single observation from OCO2. And as the figure shows, and we showed on the last slide, for each one of these footprints, we get the spectrum of radiances at different wavelengths. And so we have that for each footprint as OCO2 observes. So sometimes these single observations are called a sounding, and the spatial extent is called a footprint. So both OCO2 and OCO3 have pretty substantial coverage globally, which we'll show in a moment. And that really helps provide additional insight for the carbon cycle. And I mentioned the work by Noel Cressy that talked about this. And as we talked about on the last slide, OCO2 now has been in orbit for 8 years and will hopefully last several more years. And it's going to help answer some of these questions that will the oceans and the land biosphere in particular sort of maintain the rate of uptake of carbon from perturbations to the carbon cycle. Okay, so here's sort of a pictorial view of this data product pipeline for OCO2. On the top is the example radiant spectra, the Y, for a single footprint. I guess I haven't mentioned this yet. The 3 different panels here represent 3 different bands in the infrared part of the spectrum that OCO2 observes. And I'll talk about the importance of those shortly. Down below that is an example level 2 collection. These are estimates of CO2 at these footprints along the track of OCO2. The track itself is pretty narrow, as you can see in the figure there. This happens to be over, I think, somewhere in eastern Wyoming was this particular track. Then level 3, an example of level 3 is up here in the top right, is some sort of spatial aggregation of the level 2 products. And then finally, level 4 example on the bottom right here, these are example estimates of these fluxes between the land and ocean and the atmosphere. So the convention here is negative value. The convention is that the sign of these fluxes is relative to the atmosphere. So a negative value means that carbon is being taken up by the land or the ocean from the atmosphere, and red positive values are releases of carbon, net releases of carbon into the atmosphere. So this is just an example over a 1-year period during the OCO2 mission. Question, yes.
You have a CO2, but first, like, how much resolution can you get for the last map? And also, when you have a CO2, what depth, what level of the atmosphere are you able to penetrate? At what level are you looking at?
Yeah, good question. So one question was sort of what resolution can we get for maps like this? And I don't think I'll say much more about this later, but I think for these global type estimates, I think the carbon cycle community is trying to get these at resolution of maybe a few hundred kilometers. So it's difficult to resolve individual sources in that paradigm, but certainly subcontinental scale fluxes can be resolved from this. And then the second question was, what are we actually trying to estimate in basically in that column or that vertical path from the ground to the satellite in terms of CO2? So what I'm showing here is something called XCO2, which is basically a column average concentration of CO2 along that path that you asked about. And that's the primary quantity of interest for these missions. They do make some attempt to sort of resolve that more finely in the vertical, and get more information about CO2 near the surface versus higher up in the atmosphere, but that's a bit more challenging. Yep. Any other questions at this point? Okay. All right, so yeah, so here's a little bit more on the observing strategy and sort of how things kind of are working conceptually. So the little cartoon satellite is OCO2 or OCO3 up here. And basically they're observing reflected sunlight at the top of the atmosphere. And of course, as that radiation sort of comes from the sun and interacts with the atmosphere and the surface, a lot of different things can happen. There's the key thing that these missions are interested in is that there's absorption of radiation by gases in the atmosphere, carbon dioxide and oxygen, among others. There can be scattering of radiation by things like aerosols and clouds in the atmosphere. And then there's absorption and reflection off of the surface as well. So the inference for these missions needs to account for some of these things in an appropriate way. And so as we just talked about for OCO2 and OCO3, the primary quantity of interest is XCO2, which is sort of in mathematical terms is basically kind of a column average concentration of CO2 along that vertical path. In terms of, in a physical sense, it's really along that vertical column, it's the total molecules of CO2 divided by the total molecules of dry air. And so this is where, and that's often represented as a fraction or a proportion, and usually reported in parts per million, because the relative concentration is in an absolute sense pretty small, but it is variable, and so it's reported in that parts per million unit. And to get this denominator, that's where information about oxygen can be useful, because the relative abundance of oxygen in the atmosphere is relatively constant. Okay, so a little bit more on the observing approach. So on the right here is just a figure that shows a part of the EM spectrum. Mostly, I think what we're looking at is in the infrared, and this sort of part of the spectrum is in the infrared. We're starting to get out to microwave over here and close to visible over here. And so there's 3 vertical bars in here, a blue, a green, and red, and those are the 3 narrow bands of the spectrum that these instruments observe, and produces those 3 panels of the radiances that we saw on the previous slide. And OCO2 has been up in a polar orbit on its own satellite since 2014. OCO3 was installed on the International Space Station in 2019. So those 2 instruments and their respective observing patterns yield to different patterns in space and time in terms of the observations they collect, and that's what we're looking at on these maps. So the 2 rows are just 2 different days that I selected in 2020, and then the columns on the left is the observations from OCO2 on that day, and then the right is OCO3. And so OCO2 sort of has this regular sort of pole to pole observing pattern. So each one of these lines is essentially a single orbit of OCO2. It's sort of colored in by the time of day, and OCO2 is so-called sun synchronous, which means that at any given time, it's essentially observing at the early afternoon, just after noon local time. So if there were to be, there certainly is an orbit that will be going over the eastern and central United States at some point in the next, probably in the next couple of hours. OCO3 follows the orbit pattern of the space station, which is a bit more irregular. And you can kind of see that it's a so-called precessing orbit. And so it yields a different sort of observing pattern. And then the ISS orbit sort of has an northward limit of 50 degrees north. So that we get a lot of observations in that range, but nothing further north from that due to the ISS orbit. The other thing that this irregular orbit leads to is the OCO3 observations are often collected at different times of day, which is a difference between OCO2 and OCO3. Okay, so that's sort of the overview of the instruments. The next section, I'm going to talk a little bit about this level 2 inverse problem and some work we've done on uncertainty quantification for that. And so this is work that's been going on at JPL with the OCO2 and OCO3 teams, and Amy and Joachim are colleagues of mine in our group at JPL. So a couple of high-level points here. The data products, particularly after level 1, are really inferences. And that's an important thing to keep in mind, particularly from uncertainty quantification standpoint. And then this retrieval, there's this so-called retrieval, which is the inference from going from level 1 to level 2, and that's the terminology used in the remote sensing community. So the objective in this problem is to infer unknown quantities about the surface and the atmosphere, some of the things we saw a few slides back, from the remote sensing observations. So from a probabilistic standpoint, we might think of that as trying to characterize the distribution of the state, which we'll call X, given the radiances, which we call Y. And that I'll talk a little bit more about what goes into that X, that state, but certainly CO2 is part of that, and a key part of that for these two missions. So this process really needs to combine scientific knowledge with statistical and computational tools. And both the statistical and the computational pieces of that are pretty important. OCO2 and OCO3 are collecting essentially millions of these soundings every day, and so the computational considerations are certainly important. So if we take a sort of probabilistic perspective, that can give us some guidance on the inference in this problem. So the scientific knowledge can be in part encapsulated on a distribution on X, as well as our physical understanding of those different interactions of the radiation in the atmosphere can be encapsulated in a conditional distribution of the radiances given the state. And so here's kind of a schematic of how the observing system might actually work. There is sort of a true state, which includes the CO2 and other things in the atmosphere that the radiation is interacting with. What we actually observe, there may be sort of a true radiance, but we actually observe kind of a noisy version of that in level 2 products. And then the goal in level 2 is to infer the true state given those radiances. And that's what we'll call X hat, is our estimate of that. So how does this work more formally? So that state vector X includes a vertical profile of CO2, like we talked about earlier. Formally, in the operational setup, that includes about 20 vertical levels going from the surface to the top of the atmosphere. And then there's other key state variables in this state vector. Some atmospheric properties, some surface properties, and a few instrument-specific properties. The statistical setup is actually sort of basically kind of a hierarchical model. We assume a distribution on the state that happens to be multivariate normal. There's a mean on that, mu, which we'll call mu A, and then a covariance sigma A. And then y, basically y given x is also assumed to be multivariate Gaussian. The mean is a sort of complex nonlinear function of x and some additional parameters b, and then there's a sort of noise covariance on that s sub epsilon. So that's kind of the layout. Then to actually carry out the estimation with observed radiances, there is basically a minimization of a cost function, which is essentially proportional to the posterior distribution for x given y in this setup. The nonlinear model here, F, sort of complicates things a little bit, so there's not an analytic result that can be extracted. So what's, and I guess right here there should be a sigma A. How this is done operationally is that this cost function is optimized using a nonlinear least squares type approach to come up with an estimate x hat. And I'm going to call it x hat raw. So this is basically the result of this retrieval algorithm. And I'll talk a little bit more about some consequences from that shortly. Then if we want to get that XCO2, there's actually, based on how we've discretized that column, we can actually apply some known weights to average that column to get an estimate of XCO2. I saw a question over here, possibly, yeah.
How well is F known?
How well is F known? That's a good question. So let me just put, so F, I'll first say a bit about what F is. F is basically a radiative transfer model that captures those interactions we were talking about earlier. And I think the fundamental physics, I think the community would acknowledge are reasonably well known, but not perfectly. One of the, I think, more substantial challenges for OCO2 and OCO3 are these parameters B that are also inputs to that F, and those are also known reasonably well, but not perfectly, and they can really impact how the retrieval performs. Yep. Yes.
So in this optimization, you're going to treat the F as something unknown or known?
In this, the way it's laid out here, it's treated as known. I'll talk about how we sort of deal with that in the UQ shortly. Yeah. Other questions? Yeah.
So is mu A known?
Yeah, so excellent question. So in the operational retrieval, let's say mu A is fixed. Is it known? I don't think so. But in this operational setup, it's fixed at a specific value. So there are this is kind of the operational setup that the projects use. And there are some, I think all of you have raised some of the key areas, like from a standpoint, a statistical standpoint or UQ standpoint, you might try to probe the impact of imperfect knowledge about some of these parameters. Yeah. Yes.
When was this model to fit the spatial data or is it spatial temporal data?
It's spatiotemporal. However, this is performed one footprint at a time operationally. So it's sort of one of those spatial footprints at a time.
But
I'll talk. Yeah. So,
it's temporal.
yes. Yeah. So I mean, X and Y are fundamentally both functions of space and time. Yeah.
It's not parameters, it's the global parameters for all the locations or including the spatial parameters.
Good question. So in the operational pipeline, so let me just add quickly here. So basically, this is sort of the recipe for what's done operationally to go from level 1 to level 2. And mu A in particular varies in space and time. And you can sort of think about it as it's kind of a prior knowledge about CO2, which there is, which does vary spatially and has trends in time. And that a lot of that is captured in the mu A. And the B as well, some of those vary in space and time as well. Yeah. Other questions? Yes.
Are the covariance matrices known because the cost function that you have is not really the negative log like log. I mean, like not the negative log like.
So again, the covariance matrix is fixed as well. Yeah. Was there another question back there? Okay. All right. Yeah. So good question. So this is kind of the operational pipeline, and I think we've sort of probed at what some of the implications for UQ are. Okay. So as a result of some of those assumptions that are made, what actually is found to be the case is that this X hat CO2 is biased. The most noticeable aspect is that it's biased low globally, and there are some regional and seasonal biases that show up as well. Operationally, what happens is there are a collection of validation sites called TCON that are located around the globe, mostly in land areas, and there's a bias correction procedure that's applied to get a sort of a bias corrected XCO2 that's made available to the science community. This also has impacts on how we think about this for UQ. I'll try to get through this relatively quickly because there's a few other things I want to talk about. But one of the things that we've done on our team at JPL is to sort of take a UQ perspective to this retrieval pipeline. And we've done it using essentially Monte Carlo simulation. And that's basically schematically illustrated at the bottom here, where we take a probabilistic perspective and try to simulate the operational data processing pipeline. And because of some of the things we talked about on the last couple of slides, we try to inject some realistic sources of uncertainty into the simulation. And a big one that we've spent a lot of time on recently is in this step, we generate synthetic radiant spectra. And we actually we use the forward model F from before, but based on analysis from the bias correction and also from the operational data, we've also estimated a model discrepancy, which we call delta here. So in the simulation, we also inject this discrepancy to try and mimic that imperfect knowledge about some of those parameters. And what we get at the end of the day is a collection of joint distributions down here at the bottom that we can interrogate. And we paid particular focus to this distribution of the true state given the retrieve state, X given X hat, and have some tools to apply that to the operational data products. So here's sort of an illustration of what that looks like. I think this is the same map from OCO2 from before. I chose this because on essentially the same day, around the same time, OCO3 had an overpass close to that same area. This happens infrequently, but occasionally between the two satellites, and it's an interesting opportunity to compare them. Our procedure for UQ allows us to produce basically a collection of these distributions, which I've shown some examples of for OCO2 on the left here, OCO3 on the right, and we have the capability to produce this for the operational pipeline. And I think I had a reference to the methodology. Amy Braverman led a paper on this last year that's in the Journal on Uncertainty Quantification. But there's still there's still some remaining challenges here. As the question addressed a few minutes ago, this is still sort of all one footprint at a time, and we might need to deal with spatial dependence as well. So that brings me to the other sort of part of the work I wanted to talk about, which is some work we've been doing with Texas A&M, in fact, and some others. So there's a number of collaborators I've listed here, including Dr. Katzfuss and Anirban, who's a graduate student here, and former graduate student Daniel Zilber also contributed to this. And we also have some JPL collaborators, and the work originated during a SAMC working group a number of years ago as well. So the idea here basically is motivated by the fact that the state vectors are likely spatially correlated. And even in doing this sort of one footprint at a time retrieval approach, some diagnostics of that bias correction and the retrieval errors really do show that the errors in those retrievals are correlated spatially. The other interesting aspect of this is that the extent of spatial dependence is probably going to be different for different vertical levels in the atmosphere, as well as different parts of that state vector. So we had this work led to a paper in the journal Remote Sensing that came out last year. Basically, the idea comes down to a modification of the statistical model, where instead of considering a single footprint at a time, we'll sort of represent the spatial dependence and incorporate it by having a sort of joint model for the state that encapsulates spatial dependence as well as correlation within the state vector for a single footprint. So we could potentially apply this to a little small area of a single orbit for OCO2 that looks like this. And so that's kind of the approach that we took, was to sort of look at the level 1 to level 2 problem jointly over a spatial region. So we need a covariance that reflects both the spatial dependence and the multivariate dependence within the state vector. So to the latter point, this figure on the right was something that Anirban put together last year that sort of illustrates the correlation structure of the state for a single footprint. So, you know, reds are strong positive correlations, blues are negative. And just to orient ourselves, so this little block up here in the upper left is basically that vertical profile of carbon dioxide and how that's correlated. This sort of middle part are surface, are aerosols, atmospheric aerosols, which are also included in that state vector. And then this little block right here is surface reflectance. That's also part of the state vector. And so there are varying magnitudes of correlation within that state vector that we want to take account for. So some of the elements of the state vector that I just walked through are listed over here. And they're all included in that retrieval state. So in this work on the sort of spatial retrieval, we also attempted to incorporate and estimate the magnitude of the spatial dependence for the different elements of the state vector as well within these small areas. And so that's kind of illustrated at the bottom of the slide here. Along the x-axis are different elements of that state vector. And then what's plotted is an estimate of the range parameter in, say, a Matern covariance model for OCO2 data for those different elements. The different symbols here are just different orbits of OCO2 that we applied this to. And so for some of the atmospheric parameters like the CO2 in particular, the range of that spatial correlation can be kind of long, but some of the surface elements, that range is a bit shorter. And so in setting up this approach, we wanted to encapsulate that sort of different behavior among the state vector elements. So what we have, this sigma t that I put up here, is basically a covariance that encapsulates this multivariate spatial covariance structure. And the CT is actually a correlation. The ST is just a diagonal matrix with standard deviations in it. And then, so we had to, in addition to estimating the parameters here, we had to apply an additional low rank approximation to get sort of a resulting sigma t. Then what we did is we basically extended that simulation notion to a spatial collection of footprints, like we saw a couple of slides back. And so we simulate basically a small area of state vectors using that sigma t and an appropriate mean vector, and then apply different versions of that retrieval. In this work, we used a linear approximation to the forward model to keep things tractable. And another key point here, which we already talked about a while back, is that the realistic scenario here is that the mean of the true process is not necessarily going to be equal to that mean that's assumed in the retrieval. And then there are impacts and consequences of that with respect to retrieval bias. And so in our simulations, this figure at the bottom just sort of illustrates how we implemented that with the CO2. The solid lines are the assumed mu A, and then the dashed lines are what we used as the data generating mean vector. And so additional options then for, we need to then also assume in the retrieval a covariance jointly across the collection of spatial locations. That's what we'll call sigma A, and we've got some options there as well. So we did investigate what if we put in that true covariance that we actually simulated the data from. The second option is the so-called operational case, where we just use the single footprint at a time approach, where we assume no spatial correlation. And then the third option is sort of it's a bit of a hybrid in the sense that we impose the spatial correlation structure through that CT, but essentially we inflate the variances using these matrices. This matrix SA is just a diagonal matrix of standard deviations again. And we use what's used operationally, and that variance is perhaps a bit unrealistically large, but it does have some impacts on how the retrievals perform. So on the bottom, we're looking at the resulting collection of retrievals under these different approaches. And what we're looking at is the correlation matrix of retrieval errors of XCO2 under those different approaches. So the row and column indexing of the matrices here are just those sets of locations that we were looking at. And what happens is when we use this true setup, we do definitely mitigate a lot of spatial correlation in the retrieval errors. It doesn't totally disappear, but it's substantially smaller. In the operational case, we get highly spatially correlated retrieval errors, and then that kind of hybrid case, it's kind of a mix. Now, the other thing that I didn't really show here, but we took a close look at, is these different choices also impact the bias in the retrieval as well. And we're basically the short story here is in the true case, if the mu t is not equal to mu a, we're probably being too optimistic, and we're going to get some bias in the retrieval when we use this approach, the true case. However, the spatial choice on the third line there does lead to a bit less bias, and it mitigates that spatial correlation. So it's a bit of a nice compromise there. Okay, so I think we're kind of winding down here. So in terms of the level 4 inference problem, I just wanted to say a couple of quick things. We talked about it some in the reading group yesterday. What happens in the level 4 inference inverse problem is the objective there is to estimate those fluxes of carbon from the surface to the atmosphere, ocean to the atmosphere. And so that's what I'm calling W here. And it's sort of another sort of hierarchical setup where there's an assumed distribution on the fluxes, and then the data model, if you will, is for the concentrations, which have a mean that is a function of the fluxes and then some sort of correlation structure. And this operator, the B here, is kind of a complex thing as well that captures the transport of carbon dioxide through the atmosphere. Because what we actually see in terms of atmospheric CO2 at a given location is both a function of what's happening in terms of fluxes right there, as well as what's been transported through the atmosphere over a particular period of time. So this is another ongoing effort, is to characterize these fluxes using data from OCO2 and OCO3. So the plot at the bottom is just an example of a time record of these fluxes over North America over now the course of several years of OCO2 satellite retrievals. Now, going back to what we've talked about previously in the rest of the talk, these challenges in terms of characterizing uncertainty in level 2 and potential biases, of course, they have an impact on this flux inversion problem. And so that's something that the carbon cycle science community is putting a lot of focus on. Okay, so I think the last sort of technical thing I want to talk about here just briefly is, I alluded to it earlier, there's a lot of interest globally in monitoring greenhouse gases from space, and that's sort of illustrated in the figure here, which is now actually out of date. I think it was from last year, and it's kind of out of date already. But it's just sort of a timeline of past, current, and planned greenhouse gas monitoring satellites from various entities globally. So of course, so OCO2 is about third from the top there. And even though the bar, I think, stops in 2021, it's still going on and is planned to be continued. And there's a few upcoming missions that are being planned that will continue to monitor greenhouse gases from space. And so the challenge here is for carbon cycle science is to integrate these different satellite data products to get the best understanding of the carbon cycle possible. Okay, so I'll just make a couple of final remarks here. Just a few thoughts on some existing and emerging challenges. I think on the level 2, we hit on some of the key aspects already in the discussion, and in terms of things like data volume, we have to deal with the computational expense of the forward model as well, and this joint inference across the different footprints. Final point, we talked about it a little bit in the reading group yesterday. On the level 4 front, there's a lot of different choices for those transport operators B that are being used out there, and the best way to make use of that collection is kind of another challenge for statistics in UQ in this realm as well. And there is a fair bit of sort of lack of knowledge in that problem as well. So I think I'll stop there. Thank you very much. Glad to take any questions.
Thanks, John, for the very nice talk. We have time for maybe a couple of quick questions today. I'll open this up to that.
In your slide, you mentioned the three approach you will use. The first is the MCMC and the variational approach, and also the integral common filter. I wonder which one did you exactly use in your work, or you just combine the three of these approaches?
Yeah, so this is actually just a referential remark. So to a number of research groups that do these inversion, these flux inversions, and each group, by whatever experience or decisions they made, they sort of decided on one of these approaches for their inversions. This MCMC approach is relatively new, done by a group out of University of Wollongong. Yeah, so this now sort of sizable collection of these different flux inversion approaches, they can all use data from OCO2, but they make different choices on whether to be variational, ENKF, or that sort of thing, and then also some other decisions that they make for the transport in particular, as well as the prior that they use in the flux, can impact what the results that they get.
So
Yeah.
there are data products available to the public.
Yep.
What methods are being implemented and might be implemented in the future if we wanted to estimate the level 2 or level 1 data for a like that state? Is there basically publicly available data?
Yes, so let me go back. I think I had this way early on. Yeah, so OCO2 and 3 data products are available from the NASA archive here. They do have, definitely for OCO2 and OCO3, they have level 1. There's level 1 collections of the level 1 data products there, as well as the level 2 data products. And the ones that are publicly available are using that sort of one footprint at a time nonlinear least squares approach that we talked about halfway through. The results of that retrieval are what are made available as public level 2 products. Yep.
Does NASA have plans to update to spatially correlated results? Would you agree?
Good question. I don't know of any specific plans yet. That work I talked about there is sort of a research effort at this point. But I think it's something that will be continued to be discussed. And actually, I would say the prospects for it happening, like for OCO2 and OCO3, maybe not that great, but this method, I think, will have value for some of these Earth System Observatory missions that are also thinking about those types of techniques, and they may see some use there. In particular, I'll highlight, I've worked a little bit on what's called surface biology and geology as one of the missions that's being planned, and I think they're thinking about some of these types of approaches in that mission. Yeah.
So there are different missions that all launch different times. Some of them might add prematurely to the greater context. Especially since the OCO3 is based on the space station, which has latitudinal, differences compared to OCO2. What issues of like this type of continuity gaps do you expect for these types of problems? So I get, like, for instance, as the Arctic Ocean continues to the cover, you might expect more carbon change, and OCO3 can't capture that.
Exactly. Yeah.
Right. From a mission standpoint, what are the issues going on?
Yeah, I mean, I think you said it really well there. I mean, those types of challenges are the types of things that the carbon cycle science community is thinking about. To address some of those things, there are different organizations that are thinking about the specific problem you mentioned, which is monitoring greenhouse gases in the polar regions, because they're changing most quickly and have the potential for substantial impact. And NASA and other international agencies are thinking about other types of observing remote sensing assets that could be deployed to more to monitor the polar regions more carefully. I forget that there's a certain type of orbit that would be more conducive to monitoring the polar regions in finer resolution that's being discussed. Yeah.
Are there any other questions for John? Well, if not, let's thank John.